How do we know when to stop iterating? To understand that, I'll go back to the channel flow example. And for mass conservation for that cell, we got an algebraic equation that looked like that, of that form. And if I had the exact solution to my set of algebraic equations and I took that and plugged it into the left-hand side, the right-hand side would be 0. That would, all equal to 0, which means that the mass entering would be equal to the mass leaving in a discrete sense. But after each iteration, I don't have the exact solution to the algebraic equations. I have an approximate solution. And so my solution to the algebraic equations after each iteration will satisfy an equation that looks like that. That is, if I take my current solution after any iteration and I take the corresponding values here and plug it in here into the left-hand side, the right-hand side will not be equal to 0. It'll be equal to it'll be equal to a non-zero value, which is an error. And to indicate that this is my current solution, I will annotate it. So here's my annotation. So that's my current solution. That's my current solution for U2, current solution for V1 and V3, and they won't, all kind of add up to a 0 mass imbalance. And I'm going to get a similar error for, all these other cells. And what I need is an aggregate measure over all the cells. So here's how I define an aggregate imbalance. I've written down the equation here and I'll unpack it for you. So that's an aggregate mass imbalance, or a mass residual. It's also referred to as the continuity residual. Let's focus on the numerator first. What I'm doing here is I'm taking the absolute value of the mass residual for each cell and I'm adding it all up. So I'm going to each cell and I'm taking the absolute value of the mass residual and then adding it all up. And I'm taking the absolute value because whether this residual is positive or negative, it's an error. It's a mass imbalance. So the numerator gives me an aggregate mass imbalance, and then I scale it using a scaling factor. And the reason you need to scale is that what would seem like a small mass imbalance for a supersonic flow might be a large imbalance for a low speed flow. So the scaling factor ensures that what you're looking at is the aggregate mass imbalance relative to the aggregate kind of mass inflow or mass flow to each cell. We won't, I won't talk about the details of how the scaling is done and so on. It's not that important, at least at this point. And we'll deal with it when we are in the solver, if we have to. And we will stop iterating when this aggregate mass imbalance is less than some tolerance. And the tolerance, the default is 10 to the power of minus 3 in the Fluent solver, and we can change that. In fact, we will do that. So that's how we'll stop iterations. And the same idea applies to the momentum equation too. So if you're looking at x momentum, the net x momentum, outflow should be balanced by the net forces in the x direction on the control volume. And any part of the momentum outflow that's not balanced by the forces is an error. It's a momentum residual. And so you can understand the momentum residual by analogy to the mass residual.